I'm going to prove one direction of the Heine Borel theorem, which says that a set is compact if and only if it's closed and bounded. I will have you refer you to the book for the definition of compact. Well, maybe I'll tell you it verbally. It's compact if every sequence has a subsequence that converges to a limit that's also in K. So I'm going to assume that it has this property, every sequence has a subsequence that converges to something in K, and I'm going to prove it's closed and bounded. To prove it's bounded, the way I'm going to do this is I'm going to suppose not for contradiction. Then, the idea behind the proof is look at this picture here. Here's the number line. If it's not bounded, I can't find any sort of an m and negative n such that k is completely trapped between there. So these are impossible to find is what I'm assuming. Well then what I'm going to do is I'm just going to look at the number line 1, 2, and I'm going to look at the integers 4, 5, all the way up to n. N plus 1. And here's the deal. If k is not bounded, I can find an x1 maybe in there that's bigger than 1. x1 belongs to k and is bigger than 1. I can find an x2 that's beyond 2. If I can't find an x2 that's beyond 2, then I let m equal to 2 and I'm done. And it's bounded. But I'm supposing it's not bounded. So x2 is bigger than 2 and it's in k. x3 is bigger than 3. xn is bigger than n, etc. So this gives me a sequence xn such that xn is bigger than n, for all natural numbers n. Okay, so this is a sequence that's in k, and I built it up because I knew that it was bounded, because I'm supposing it's not, I'm supposing it's not bounded, so I can build it. Compact says that any sort of a sequence, like this one right here, should have a convergent subsequence. So there should be a convergent subsequence that goes to some sort of x belonging to k. But we know that convergent subsequences are bounded. Convergent sequences are bounded. Must be bounded. But it still has this property over here where x sub subscript is bigger than or equal to subscript. But x sub nj is bigger than nj, and there are infinitely many of them. So these x sub nj's are getting bigger and bigger and bigger. So if it converges, it's got to be bounded. But by construction of this, every subsequence is going to be unbounded. So that's a contradiction. What does it contradict? It contradicted the fact that the original sequence was not bounded. So that's why. So what I've done is I've proved that if it says compact, then it has to be bounded. If it's not bounded, then it won't be compact, because I'll be able to find this sequence with a subsequence where no subsequence converges. All right, for closed, what I'm going to do is I'm going to look at a limit point of k. Well, one way of thinking about limit points is that there must be a sequence that belongs to k. X is not equal to xn for all n, but xn goes to x. Right? That's a theorem. A theorem says that x is a limit point for k if and only if these things hold. Well, what do we know? I know that k is compact. So x is a limit point, and we have this sequence in k converging to x. It has to have convergent subsequence, well, wait, it does because it's bounded. But what we're going to do is we're going to, we know that it has a convergent subsequence that also converges to x, because it's compact. That's what compact means. Moreover, because it's compact, this thing has to converge to something in k. So a converging sequence, all subsequences converge to the same thing. But because k is compact, its subsequent converges to x, which is in k. So compactness gets us within k, which means it contains its limit points, so it's closed.